Hello and welcome back to Introduction to Number Theory. In this video, we begin our study of quadratic irrationalities, which will lead us to Pell's equations. Well, you might have already noticed that there are different types of quadratic irrationalities. There are integer irrationalities with integer coefficients and rational irrationalities with rational coefficients. Well, within this lesson, we will deal with integer quadratic irrationalities. So let's begin with the definition. First, we take an integer, actually a positive integer, a natural number a, which is not square, so it is not equal to any b square where b is an integer. This certainly means that square root of a is irrational. So with this a, we can form a set of numbers of the form x plus y square root of a, where x and y are integers, and further on we'll study this set of numbers. Well, all these numbers are certainly real numbers. Not all of them are irrational, of course, because y can be equal to 0. So some of them are integer. Let's take a look at this set of numbers in a certain example. For instance, if a is equal to 2, then of course a is not perfect square, so square root of 2 is irrational. And let's mark the points on the real line that correspond to numbers of the form x plus y square root of 2. Well, we see different points, and we understand that this set is, well, somehow dense within the set of real numbers. Actually, we can prove it using the Kroneker's theorem that the set of quadratic irrationalities is everywhere dense. However, while looking at this example, we might ask ourselves, well, is it possible that a certain real number can be represented in the form x plus y square root of a in several different ways? Well, is this representation unique? This leads us to the second part of our fragment, which is called the uniqueness of the representation. Well, it turns out that the representation is indeed unique. Let us show this. So suppose that some real number z is represented as x1 plus y1 square root of a, and at the same time it is represented as x2 plus y2 square root of a. So by this we assume that there are two different representations of the same real number z. We will prove that in this case x1 is equal to x2 and y1 is equal to y2, so it is actually the same representation. Indeed, let's form an equation that connects the first and the second representation. And then let's put all summands that contain square root of a in the one hand side, and all summands that do not contain square root of a. Let's put them to the other hand side of this equation. So we gain that the difference of x's is equal to the difference of y's multiplied by square root of a. Now, as I believe you already understand, we can divide this equation by the difference of y's and gain that square root of a is equal to this fraction. Well, you understand that such fraction, since x1, x2, y1, y2 are integers, this fraction is actually rational. But this leads us to a contradiction, because we know that the square root of a is not rational. What does this mean? Well, this means that something's wrong with our assumption. Well, where is this wrong assumption? Of course, when we divide it by y2 minus y1, because we know that division is possible only if we are going to divide by something that is not 0. So we get to a contradiction unless y2 minus y1 is equal to 0, which means that the y's are equal to each other. And of course, in this case, x's are also equal to each other. So this finishes the proof of the uniqueness of the representation. Every number that can be represented as integer plus integer multiplied by square root of a can be represented in this way, the unique way.